So which problem in particular?
Um, 19.
Okay. Scroll down. Getting close, getting close. And there's 19.
Mhm.
Okay. So let's see. Let me orient us here. Exam 2, problem 19. A 16.4 gram sample of hydrogen fluoride is dissolved in water to give 2 times 10 to the second milliliters of solution. The concentration of the solution is. So if you, this is a multiple choice question. So if you look at the answers, you see what the units of measure need to be when you finish your answer. They need to be in molarity. Okay. So there's one of the formulas that you're going to need. How do you calculate molarity? Well, useful information should tell you if you've used it enough, then you can go down to the, let's see, here we go. No, right here. Nope. Next one. Nope. I went too far. Here we go. Oh, it's not there. I guess I expect you to memorize that one. Sorry. So, how do we determine molarity? Molarity, by definition, is moles per unit volume, right? And this has to be in liters. And this, of course, is moles. Now, is that something is that the sticking point, not knowing to use that formula?
Yeah, I'm just having a little issue plugging it in.
Oh, and then what to put where?
Yeah.
Okay. All right. So if we start with the form, the answer requires, because of A through E, all that's in molarity, the answer requires that you use this formula. That's the only way you can get molarity is moles per unit volume. So the real trick is, how do you get to moles from grams, right? That takes you back to dimensional analysis, unit conversion. So we know we have 16.4 grams of HF, but we've got to turn it into moles. So you need a factor, right? This is in the numerator. So we got to get rid of the grams denominator and leave us with moles. Okay, so far so good?
Yep.
Okay. So how do we do that? Periodic table. Right? So we just say hydrogen is 1.01 grams per mole. Fluorine is 19, I believe, rounded off to two places, 19 grams per mole. So add those together and you get 20.01 grams per mole. Now, remember, this is a conversion factor, and all conversion factors are equal to 1. We don't need it grams per mole, we need it moles per gram. So 20.01 grams per 1 mole. Right? That's perfectly valid because we know that that conversion factor is equal to 1. So once we do that calculation, and I've got it there in red, 0.8196, 0.8196 moles of HF. Okay, got that part ready to go. How about the other part? 2 times 10 to the second milliliters. That's in the wrong units. You need liters. So what's 2 times 10 to the second milliliters? Times 10 to the second milliliters. We need to convert that into liters. Now, if you know how many milliliters in a liter, you can probably do it in your head. But if you just want to be safe, we can do another unit conversion. right? Numerator, denominator. That's what we get in the end, because these cancel. And just like those canceled. So what's the relationship here? 1 liter is 1,000 milliliters, right? So if we divide 1,000 into this is 10 to the third in the denominator, 10 to the minus third in the numerator. So that would be 2 times 10 to the minus 1 liters. Or 0.20 liters. Now we got that. Okay, so from there, we've done all the hard thinking part. We just need to plug the numbers in and crunch. 8196 moles per 0.20 liters. And since we only have 2 significant figures here, we're going to end up with, let's do it. Let's do it the long way instead of going to, let's see, 0.8196 divided by 0.2. So that gives me 4.0980 molar. So we got to round it off to 2 places. We're going to round it off to here. That means this has to be 4.1. And those go away. This type of problem is typical in chemistry, because in the laboratory, you're going to make measurements in whatever units are available, right? HF, we're going to measure that in grams. Actually, hydrogen fluoride is a gas. We're probably going to measure it in volume. And then we would have to convert it into mass. But that's an extension of this problem. What you're given is mass. And we're also going to measure in milliliters, because most devices in the lab are in milliliters, not liters. So you're going to need to be able to convert.
Okay, thank you.
Did that help any?
It did. Seeing it worked out, that made a little bit more sense.
Okay, yeah. And like I said at the very beginning of the course, when we started talking about dimensional analysis, lots of problems, at least half of the chemistry problems that you're ever going to encounter are solvable through dimensional analysis, through unit conversions. Okay. Next. Are we going to stay in the exam?
Yes.
Okay. So let's make room for the next one. All right. What number are we headed for?
22.
Okay. Scroll down to 22. All right. So we've got these 2 reactions. I might as well put them on the board. And that's it's aqueous, and then we get a solid. Okay. Aqueous. And then 2 silver nitrates react to form what? Well, let's look at this. Will help you identify what type of reaction this is. Right? We've got a solution here of these 2 ionic compounds. So what are they going to be doing in solution? they're gonna be separate ions, right? We're gonna have a zinc ion, we're gonna have bromides, we're gonna have silver ions and nitrate ions in solution. So they can swap places. This is a double replacement reaction. So when silver encounters bromine, it precipitates. That's why it's a solid. And then what's left over? Zinc and nitrate. Zinc and nitrate, and that's soluble. Now, you don't have to go that far, but if you're given just this part of the reaction, you can generate that part. Simple. And it's balanced for you. Okay, how about this one? KBr and silver nitrate. KBr aqueous and silver nitrate aqueous. And that gives us, again, silver bromide and potassium nitrate. Okay, so what do these two reactions have in common? They're both double replacements. Right? Individual ions in solution are able to swap. Silver encounters bromine, precipitates. Potassium encounters nitrate. They don't care. They're spectators. Right? They stay in solution, both sides. Okay, so what does that say about the type of reaction you've got here? Well, first of all, you're precipitating. This is a precipitation reaction. Both of them are precipitation reactions. Now, are they acid-base reactions? No, we don't have any acids in here. We don't have any bases in here, right? Where are the hydrogens? There are no hydrogens in that reaction, so it can't be acid-base. Right? Precipitation, oxidation reduction. How do we know whether it's oxidation reduction or not? Electrons must be transferred. You have to change oxidation states in order to get a redox reaction. So in solution, this is going to be a -1, right? Because all halogens are -1 in ionic compounds. That makes this one, since it's 2 minuses, that one has to be 2+. This one is a polyatomic ion, and silver can only have one charge, right? It's one of those, right, that has a fixed charge. Right, on this side, that didn't change. This didn't change. That didn't change. And something's wrong here. Yep. I got my formula wrong. So this one is 2 pluses. So did their oxidation states change? Remember, oxidation states for ions are the charge on the ion. So 2+, none of that changed. So that's not an oxidation reduction reaction. You do the same thing for this one and find that it's not oxidation reduction. So the only valid one for that is precipitation, because you get two solutions mixed together and you produce a solid. That's precipitation. You gonna sign in? Okay. I think we're in the second exam right now, chapters 3 and 4, looking at, and this is student driven, right? You guys tell me what to do and we'll talk about the problems. Now we, up to this point, we've decided that math itself is not the problem. It's applying the math. Is that true for you guys too? Or is math, basic math, also a problem?
application, I would say, because depending on some of the questions that I come across, I have a hard time figuring out what goes where.
Okay. So y'all are in the same boat. Okay. Another one, number 9. Okay. Let's go back. Scroll. And there's number 9. All right. 5.95 gram sample of silver nitrate is reacted with barium chloride according to this equation. So we got an aqueous solution of barium chloride, an aqueous solution of silver nitrate separate. Then we put them together and we get a precipitate, silver chloride, and barium nitrate is spectator, it's still in solution. And the end product is 3.17 grams of silver chloride. The expected theoretical yield of silver chloride is 5.02 grams. What percent yield? All right. So this one could have been a whole lot more difficult than it is. I could have said, and not given you the expected yield. And you calculate the yield yourself. What's the theoretical yield of silver chloride before you can answer the question? But I had mercy on you and gave you the theoretical yield as 5.02 grams. So what that means is a lot of this problem is blue smoke. You don't need to know it. All you need to know is that the actual amount is 3.17 grams and the theoretical amount is 5.02 grams. So percent yield equals the actual divided by the theoretical times 100. Usually that'll be in grams. Sometimes it'll be in moles, but grams is more typical of what you will see. So now all you need to know is, and I mean, this is overkill, but for some problems, it's necessary to extract information from a word problem so that you don't put numbers in the wrong place. So what do we got here? 3.17 grams of silver chloride were produced by this reaction. So what value does that relate to? Is that actual or theoretical?
That'd be the actual.
Yep. So the theoretical has to be 5.02 grams. So this is theoretical. Now you can plug the numbers in here and not get it wrong. And by the way, most of the time, not all the time, but most of the time, the actual is going to be less than the theoretical. If the actual is higher than the theoretical, then there's something wrong with the experiment. Like say you produced a product that's not fully dried. We get this precipitate, silver chloride, and it's still surrounded by water molecules. So you got to dry it down before you can weigh it. So if you don't dry it completely, you may have some water hanging on, and that would elevate the actual above the theoretical. So you could get higher than 100%. But typically, if you do your procedure correctly, you should get something less than 100%. And if we plug the values in here, 3.17 here and 5.02 there, then we should get 63.1%. Did we answer your question? Yeah. Okay. Y'all got your symbols memorized? Good deal. Feel comfortable with naming compounds?
Still. That.
Still working on that? Okay. Let's see, we've got, is this the chapter with the extra credit, 50 ways to name your compound, or was that with?
That was the first one.
That was chapter 1 and 2. Okay. I know everybody hasn't been turning in extra credits, and that seems a shame because they can help you out of a deep hole. Okay, another one. I mean, we can, yeah, go ahead.
Oh, okay. Well, you can go ahead if you want.
Well, I was just going to say, we can stay in exam 2 for a while if you want, if you got several, and then we can migrate to some other. I mean, we don't even have to work from a document. I mean, you can pull one out of homework or out of the textbook, whatever you want to do, and we'll deal with it. Did you have one, Kaylee?
Yes, I'm sorry to keep flipping back.
You know, you can, in most cases, if you're muted, you can just touch the space bar and hold it down and talk, and then when you let it up, you're muted again.
Oh, I didn't realize that. That's one of my first times using this.
It's a little simpler than having to go to the mute thing and click on it every time.
Okay. Well, working on 19 kind of helped with 20,
Okay.
but I did have another one in here.
Okay.
Someone else can go if they would like.
Oh yeah. Yeah. Okay.
Not sure where it is.
Okay. Anybody else while Kaylee's looking hers up?
Oh, I have it.
I think I'm just having trouble balancing.
Balancing equations? Okay. So let's see, that would be, let's see, I just passed one, didn't I? Which one? Oh, actually balancing equations. Okay, so let's go on down. And nope, not quite. Keep going. Okay, that's empirical and molecular formulas. Do you have a number?
Oh, there's
Here's yep. 115. Number 15. Okay. Go back up. There we go. Okay. Oh. You can't balance that equation until you figure out what the names are, or what the formulas are for the names. Is that the problem? Or one of the problems?
I think that's also one.
Yeah. Okay. So, let's do 15. All right, the problem is a reaction occurs between sodium carbonate and hydrochloric acid. So, sodium, right? What's the symbol for sodium? Uh-huh. And how about carbonate? That's a polyatomic ion, isn't it? So you can look that one up. I'll wait. There it is. Yep. CO3. What? Just a 2? Yeah, there you go. And how about sodium? What's its charge? Does it have a fixed charge? Or is it variable?
Say +1.
+1 all the time, right? Okay. So now we can balance the charges. This is an ionic compound. sodium is a 1+, and that's a 2-, so we need 2 sodiums, right? Okay, that's the first step. Get your compounds written correctly. Okay, so that is going to react with hydrochloric acid. And sodium chloride is sodium carbonate's a solid. Hydrochloric acid is what? There's got to be an aqueous solution, doesn't it? Okay. So if we're going to say hydrochloric, when we say hydro, what does that mean in the name of an acid? It means there's no oxygen. Right? So we go to, we know it starts with H because it's an acid. And how do we get chloric out of that? Ides become X. So hydrogen chloride, like that, right? 1 and plus. Hydrogen chloride in aqueous solution is hydrochloric acid. Does that mess with your brain too? Okay.
So I also am having trouble.
Yeah. The only way to get around that is practice. Yeah. Just make mistakes, figure out what you did wrong, and don't do it again. And just keep doing that, practicing. And that depends for a lot of my students, not most of them, but a lot of my students have other responsibilities. I mean, some of them have families, like small children. Some of them have jobs, like most of them have jobs. And that gets in the way of your study time, right? So it's a matter of efficiency. How do you most efficiently spend time working these things? You have to block out a certain amount of time, preferably every day if you can, because chemistry is one of those things that cramming for doesn't work for 99.9% of the people. I've known a few people who could cram for an exam and succeed, but it's rare, right? You need to absorb it little at a time. And like 2 steps forward and 1 step back, and then 2 steps forward and 1 step back. So you're moving forward. It's just you're learning something, and then you check it out later to see how much you retained and you missed some things. So you work on it again and you move forward. In small increments. Okay. So, and it tells us that we produce sodium chloride out of this reaction. And it's going to be aqueous. And what's left over? HCO3, which is carbon dioxide and water. Now they actually skipped a step. We would produce carbonic acid, but it's unstable, so it produces carbon dioxide and water. Right? So the overall reaction produces this. Okay. So there's your starting point. Once you get that established, then we can work on balancing it. See, I'm going to get rid of these right here because they're kind of muddy in the waters. Okay. So with our budget method, how would you deal with this? Well, first of all, you can't use the polyatomic ion trick where you have CO3 is not on the other side. It breaks apart. So you got to have individual elements identified for each. Carbon, oxygen, hydrogen, and chlorine. And then you do your initial assessment. We have 2 sodiums, right? 1 carbon, oxygens, 3 oxygens, hydrogens, 1, and chlorines, 1. Sometimes I check myself to see if I counted them right. Right, we have 2, 3, 6, 7, 8. 2, 3, 6, 7, 8. So I got them all up there. Then we go to the other side. How many sodiums? 1. How many carbons? 1. Oxygens? 3. And hydrogens, 2. And chlorines, 1. Now you can see it's not balanced. Right? We got 2 sodiums on this side and only 1 on that side. We don't have any elements standing alone, so we can't hold any of those till later. Carbon, oxygen, okay, hydrogen, we need 2 on this side. So if I don't have intuition about where to start that will simplify the process, I just start at the top. We need 2 sodiums. So I put 2 sodiums here. That changes this to 2 and chlorine to 2. Now I come down, I need hydrogens. I need 2 hydrogens on this side, right? So that's 2 hydrogens here and 2 chlorines. And lo and behold, we're balanced. So to answer the question, the coefficients are, don't forget, just because we didn't put a 1 there doesn't mean it's not there. It's 1, 2, 2, 1, 1. So that's why the answer is D. Okay. Yeah, it's when you get a word problem like that, you have to know how to write compounds. There's no way around it. Any others? Oh, okay. Kaylee, you were looking something up. Did you find it?
Yes, so it's actually number 11 in the same exam.
Okay. All right, let's see. Back up a little bit. Here we go. I got something in my way. Let me move it out of the way there. Okay. Vitamin C. Oh, okay. We're going to go from percent composition by mass for a compound, vitamin C in this case. And we're going to determine the molecular formula for vitamin C. So, also known as ascorbic acid. How do we deal with this problem? In order to determine the molecular formula, we have to go through the empirical formula first. You've got to find the simplest whole number ratio of atoms in the formula. Right, so remember what an empirical formula is. Say if we have something like this, C6H6, right? That could be benzene. The simplest ratio of carbon to hydrogen here is 1 to 1. Right? We can divide through by 6 and get 1 to 1 ratio. Right? We could do the same thing with acetylene. Give us the same empirical formula. So empirical formula only gets you part way, but you have to do it before you can make the jump to molecular formula. So for ascorbic acid, first thing we need to know is what are the elements that are contained in ascorbic acid? And we're told carbon, hydrogen, oxygen only. Nothing else. And then we're told percentage of carbon, 40.9%, and hydrogen, 4.58% by mass. Now, why didn't it tell us oxygen? Because you can calculate it, right? If carbon, hydrogen, oxygen are the only 3 elements, and we know the composition of 2 of them, then subtract those from 100%, and that's the other one. So we can put, let's see, carbon at 40.9%. And this is by mass. So that'd be mass. Hydrogen and oxygen. And hydrogen is 4.58%. 4.58%. mass. So oxygen would be what's left over. All right, 40.9 and 4.58. So this is 45.48 here. 45.48% is accounted for by carbon and hydrogen. So the rest of it has to be oxygen. We just subtract this from 100%. And I get 54.5%. Okay, so we don't need this one anymore. We've got our percent composition, and these all together should be 100%. And they're mass. Okay. So how do we make the jump to numbers of atoms in the formula, right? That's a ratio of moles, not a ratio of mass. So these have to be converted to moles before we can go any further. There's another fly in the ointment. That's not mass. That's percent. So how do we get around that? Well, if this is 40.9 grams of carbon per 100 gram of sample, why don't we just say, all right, I got a 100-gram sample. If I got a 100-gram sample, 49.9 grams of it is carbon. And this ratio is fixed, right? The law of definite proportions. Ascorbic acid or vitamin C is always that ratio, no matter where it comes from. So if I've got 100 grams of it, let's just assume 100-gram sample. That means this is 40.9 grams of carbon and 4.58 grams of hydrogen, 54.5 grams of oxygen. Now we can work with that. We can convert that into moles. With what? What's our conversion factor? Molar mass, right? Molar mass of carbon. Right? We can convert it to moles. Or you can look at it this way, right? If I need moles over here, right? Moles. That's in the numerator, right? So that means our conversion factor has to have moles in the numerator. So if we want to get rid of grams and leave us with moles, grams has to be in the denominator. Okay. So whenever you see grams and moles in a quotient relationship, that's molar mass. So what's carbon? How many grams per mole? It's on the periodic table.
12.1.
Uh-huh.
12.0.
Yeah, rounded off to 2 decimal points. That's right. How about hydrogen?
1.01.
Uh-huh. And oxygen.
16.
Right. Okay. Now we can do some calculating. So let's see, 40.9 divided by 12.01. And I get 3.405. And I'm going to keep a few decimal places until we get this thing ironed out, just so we avoid rounding errors. And the other one, the next one, I get 4.535. And the last one, 16. I get 3.406. 406. Okay. So now, this is the simplest ratio of carbon to hydrogen to oxygen in the molecule. It's not the simplest whole number ratio, though. We need whole numbers to get the empirical formula. So what's the next step? Well, the rules of math say that if I multiply these by some number, same number, or divide them by the same number, then I haven't changed their ratio. Right? So I picked the smallest number. 3.405. Oops, 05. 3.405 and 3.405. Just divide them all by the same number. This is 1. This is so close to 1. Might as well call it 1. Right? 0.406 divided by 0.405. That's essentially 1. How about the second one? Got a number for me? Oh, I can do that. 4.535.
Got 1.332.
Okay. So, that's good enough. What that tells us is that we're homing in on a whole number ratio. Now we've got these whole numbers, okay, but we got that fraction. How do you get rid of a fraction? If you have, say, that, you want to get rid of that fraction, you multiply by the denominator, don't you? Right? If we have this one, we multiply by 3. Well, that's about a third right there. So if we multiply each one of these by 3, we're going to get rid of that fraction and leave us with a whole number. This is 3. This is 3 plus 1, right? That's 4. And this is 3. So now we have our whole number ratio for vitamin C. So it's carbon 1. Well, I don't have to write 1 in there. And hydrogen, oops, excuse me, 3, 4, and oxygen 3. There we go. 343 is our empirical formula. Okay. So next we want to go to the molecular formula. And to do that, this ratio is fixed. But the numbers of atoms in the molecule is a multiple of that. Right? So we need some value here to multiply each one of these to give us the molecular formula. So we're told that the molar mass of vitamin C is about 180 grams per mole. So if we find out what that number is, then it's going to yield 180 grams per mole if we calculate the molar mass. But it's not there yet. We need to find out what that is. So what's the molar mass of that? I call it the empirical weight. What'd you get?
8807.
Yeah, 88.07 grams per mole of that formula. So if we multiply this, and this has to be a whole number, if we multiply that times 1, that's not going to get us there. If we multiply by 2, that's pretty close. Times 2 equals 176. And notice they said about 180. So if we multiply by 3, then we go way over. So our closest approximation is going to be n equals 2. So now if we multiply 2 through that formula, we get C6H8O6. And that's our molecular formula.
Okay, the one thing I missed was, I was writing it down, I'm sorry.
Okay.
You said the 88.07, how did we get that?
We added up the molar masses of 3 carbons, 4 hydrogens, and 3 oxygens.
Okay, thank you.
This is what I call the empirical weight because it's derived from the empirical formula. And this is the one, this is actually, this one and this one are actually would be derived from the molecular formula.
Okay, that really helped. Thank you.
Okay. Okay, got any more?
Not that I can think of right here.
Okay, so are we done with exam 2? Or do you have some others? How about the balancing equation thing? Does that need more work?
I do, yeah.
Okay, let's find one that's more difficult. I think I had some at the very end, didn't I? And we haven't even talked about balanced molecular equation, complete ionic equation, and net ionic equation. Did that give you any trouble? I know some people didn't even try that question. They just blew it off. Let's see if I can find a number here. Back up, back up. Let's see. Oops. I saw it just a minute ago. Oh, we did that one already. No. Maybe it's in the maybe it was in the bonus section. In that case, blowing it off didn't cost you anything. Or maybe we didn't cover that. Maybe we didn't cover that in chapter 3 and 4. Was the net ionic equation? Did we do that? Don't remember that. Oh, okay. And stoichiometry, right, can be a problem.
And the bonus section there is a couple questions related to the net ionic equation.
Okay, where is that?
It'd be 60 through 62.
60. That's where I saw it. Here we go. All right. So in order to answer 60 through 62, we have to balance the equation in molecular form, then complete ionic form, and net ionic form. So that's what this is all about. Let's see, we're going to look at 60 through 62 based upon this word problem and what we have to derive from it. Aqueous solution of barium chloride, aqueous. Is that written correctly? What's the charge on barium?
It's +2.
Yeah, okay, so this one's that, this one's that, so I need 2 of these, don't I? 2 chlorines. Okay, and react that with silver nitrate. Silver's a +1 charge, nitrate's a -1, so that's good. And it doesn't tell you what the products are. Oh, yeah, it does. Forms silver chloride. Okay. So have mercy on silver chloride. You could figure this out though. And what's left over? Barium and nitrate. Since this is a 2+ and that's a 1-, we need that. Okay. Now, balancing. We're going to balance complete the molecular equation first and work from there. So notice that we've got this polyatomic ion that's the same on both sides. That's good because we can use that as a balancing unit. Right? I'm going to do it the long way. These equations typically are very well behaved. You can usually balance them without even going through the budget method. But I'm going to do the budget method anyway, just to be complete. So we got barium, chlorine, silver, and nitrate. I'll leave the charges off. So we got 1 barium, 2 chlorines, 1 silver, and 1 nitrate. Over here we got 1 barium, 1 chlorine, and 1 silver, and 2 nitrates. Okay. So I just start with chlorine. We need 2 chlorines on that side. So that gives us 2 chlorines and 2 silver. Okay. So now we need either 2 nitrates or 2 silvers, whichever one you pick one. 2 silvers. It also gives us 2 nitrates. Now we're balanced. Okay. So that's the complete ionic equation. The molecular equation, excuse me. Molecular equation is now balanced. Did one of these questions refer to that one? The balanced molecular equation contains which one of the following terms? Well, let's see. And notice that your answers have coefficients in them. So we have to take that into account. So this term, 2 silver chloride, would be B. Right? We don't have 2 of these. We don't have 1 of these. D is 1 of these, but it's the wrong formula. I mean, no, it's 2, right? 2, we can't do that. And BaNO3 is the wrong formula. And we don't have 3 silver chlorides. So the only one that works is B. Now, the complete ionic equation. What we have to do is recognize that in solution, these ions are free. So you need to know their charges, right? We found this one to be 2+ charge. And it's an aqueous solution. That's your first term. This one has 2 chlorides in solution. Okay? That's how barium chloride would split up. 1 barium, 2 chlorides. Sometimes that spins your head around. For this one, we have 2 silvers. They're always a +1 charge in aqueous solution. And 2 nitrates in aqueous solution. Okay? On this side, that solid does not dissociate. It stays intact. Okay? Now we have 1 barium plus, 2 barium 2+ aqueous, and we have 2 nitrates aqueous solution. Okay? That would be the complete ionic equation. And let's see, 61 says, which of the following terms is in that one? Well, let's see, 2 Ba2+ is not there. B says one chloride, no, we need two. Two silvers, yep, that one works. The nitrates are also two, so D doesn't work, and silver chloride aqueous doesn't exist. So the two silvers is the answer for 61, C. Now we need to go to the net ionic equation. So how do we get to the net? Is everybody okay up to this point? I should stop and ask that. Did you see how I got from here to here? Okay.
Mm.
Yeah, you have to know the charges on each one, and then you have to, any subscripts become coefficients in the complete ionic equation. Or if they're already coefficients, then they propagate through the entire thing. So that means that there's two silvers and two nitrates when that splits. Okay, so the net ionic equation simply crosses out the spectators. In other words, the ions that you have in solution are the same on both sides. So the best way to do that is say, all right, which one's solid? This one right here. So we got to keep this one, right? And we got to keep that one. Otherwise, we don't have a product. And then we look at the others. We've got a barium 2+ on both sides. And we got two nitrates on both sides. So the net ionic equation is, well, actually, simplest whole number ratio. We're actually not done yet, right? 2, 2, and 2, simplest ratio is 1, 1, and 1. That's the trick for this one. You don't have, in the net ionic equation, you don't have 2, 2, and 2. You have 1, 1, and 1. That's the simplest whole number ratio. So if we look at 62, the temptation, oh, wait a minute. Oh, okay. That's a good thing that's a bonus because that's wrong. The net ionic equation should be 1 silver. A would be right, but it needs to be 1 silver. And let's see. Let's see, where's my edit? Remember which version of Acrobat I'm in. So I would get rid of that. It should be that. It should be a single silver ion. How about the barium crossed out, nitrate crossed out, there's no hydrogen in there, and silver chloride aqueous doesn't exist. Okay, so with that correction, A is still the right answer. Now, for some reason, this one gets by me on a future exam. Well, let's see, we're gonna have a final. We got room for a final. Some of my classes. Yes, we do. Okay. So if I put one like this in the final and don't reduce it, then pick the best answer. Or call my attention to it. If I mark it wrong and you've got evidence that it should be that one, then sure, I'll go with it. Okay. That was some more balancing. Let's see. Everybody comfortable with oxidation states, oxidation numbers?
I wasn't here when you were going over it. Could you go over one of those real quick?
Yeah, sure. We'll talk about the rules first. let's see, we're gonna be working from 64 would be good. Work from 64. But before we do that, let's look at the rules. Elements. In most stable form at standard temperature and pressure, their oxidation number is 0. So that would be any of the metals, like if we had Ag reacted with something, it would be oxidation number of 0. Or if we have a diatomic element, like nitrogen or hydrogen or oxygen, each of those atoms would be oxidation state 0. And ions equal their charge. Okay. Any ions, any individual ions as elements. I better specify the elements as ions. Like if we had chloride ions in solution, its oxidation number would be -1. Let's see. Okay, fixed oxidation numbers. Fluorine is always -1. Oxygen in a compound, fixed in compounds. Fluorine is a -1. Oxygen is a -2. And that you'll usually find these fixed in compounds, and these are usually covalent. Because in ionic compounds, you can deduce the oxidation number, especially if you know these are -1, -2. Let's see. Oh, hydrogen. Hydrogen is +1 if first. And -1 if second with a metal. And then the exception to oxygen here is peroxides. Peroxide, where you have something with oxygen, and then something else, like R1. That's the case, then these are each -1, and both together are -2. Okay, and for the total oxidation numbers equal 0 for neutral compounds and equals the charge for polyatomics. So you add up the oxidation numbers for all of the members of the compound. If it's a neutral compound, then they all have to add up to 0. It has to be a neutral compound. If there's a charge, like a polyatomic ion, then the sum of the oxidation numbers must equal the charge on the polyatomic. Okay, all right. So now we can look at 64. Okay, which of the following does iodine have the lowest oxidation state? All right, so we've got A, B, C, D, and E, I think. Yep. So the first one is lithium iodate. Second one is iodine dioxide. Why do I name it that? Because they're both nonmetals. It's a type 3 compound. and diiodine monoxide and ammonium iodide. That's a type 1 compound, and then elemental iodine. Okay, let's take the easiest one first. The element, right? Its oxidation number would be 0 for iodine. Okay, how about this one? This one's easy because we know that ammonium is a +1 charge. It's a polyatomic ion, right? It's +1. That's -1. Okay. This one, we have to go back to our rules. Oxygen in this case is -2. -2. So this one, together, these have to be +2, but each one then would have to be a +1. If this one's a -2, then we have a total of a -4 for that. So this has to be a +4 to balance that oxidation number. Because this is a compound, they have to add up to 0. So this one has to be a +4 to balance that -4 total. And then this one, we can do it 2 ways. We can add up lithium and oxygen and whatever iodine has to be to balance to 0. Or we can say the iodate ion is a -1 and add these up to equal -1. Either way works. So this is a -2, right? Let's do it out here. We'll do it this way first. -2 here, so that's -6 total for the oxygens. And lithium is an alkali metal, so it's a +1. I didn't mention that rule. Alkali metals are always +1. Alkaline earths are always +2. Aluminum, gallium, indium, thallium. I think that's it. Thallium is +3. So this is +1, that's -6. So what do we got here? -5. So to make this compound neutral, iodine has to be +5. And if we did it this way, we know that's the iodate ion. So 3 times -2 is -6. But we need to make sure that when we add it up, we only get we get a -1 charge left over. So really, we only need to balance 5 of those and leave 1 out. So we end up the same place. And just go back and add it, right? +5 -6, -1. We're good. Okay, now to answer the question, which one has the lowest, did it say? Lowest oxidation number. So we have, let's see, what did I say this was? +5. Yeah. The lowest one is this one, D, -1. Now, the lowest one in a group may not be a negative number, right? It could be a positive number. It's just the smallest positive. Okay. Do we need to do another one? You can pick one if you want.
Another one of those would be helpful.
Okay. So let's scooch up here a little bit and see. Oxidation numbers. No. All right, I might get to it faster by using the search. Okay. We did that one already. No. There we go. 27. And there's sometimes you may have a compound that has members. And in order to deduce the one that's asked for, you may have to make an assumption about any of the others. For instance, if we had, let's see, we're headed for 27. But if you had one that was composed of, say, I don't know, sulfur and chlorine, right? Like that. Sulfur dichloride. We don't have a rule for those, right? We have oxygen, we have fluorine, but we don't have sulfur and chlorine. So I go for the halogens. If you got a halogen in a compound, I typically give it the -1 charge. So that makes this +2. Sometimes you have to make an assumption, realizing that oxidation states, this method is bookkeeping method. We're not saying that there are any charges here unless it's explicit ions, right? Then of course they have the charge. But we're just trying to keep track of electrons so that we can watch their movement. Right? We're not going to get deep into that in this course, in 101. 102, we actually balance equations using oxidation states. So that's coming if you stick around for the second semester. Okay, so the question here is, in which of the following does nitrogen have an oxidation state of +4? So we're working with HNO3, NO2, N2O, laughing gas, ammonium chloride, and sodium nitrite. So we're looking for an oxidation state, oxidation number equal to +4 for nitrogen. Okay, so hydrogen, if hydrogen comes first in the formula, it's a +1. And oxygen's -2. So we have -2 times 3 is a -6, but a +1 means we only balance a -5. So this nitrogen is a +5. Did I lose you? Okay. Here we go with -2, right? 2 of those means -4. This is a +4. We found our answer. But we can keep going just for practice. -2 here. That means each one of these two balance that one with a +2, but each one of them has to be a +1. Let's see. Let's do this one as ammonium. Right, we know that. So this is, well, I said this hydrogen, if it comes second with a metal, then it's a -1. But in this compound, I mean this polyatomic ion, it's only +1. +1 means +4 total. That means, let's see, this nitrogen would be -4, correct? Oh, no. We need to keep +1. -3, right? Because we want one of those pluses held out for the charge. So that means we only need to balance +3. This is +3. And this is +1. And then the last one, NO2, we know is NO2 minus the nitrite ion. So this is -2 times that is -4. We hold one of them out. So we only balance plus 3, so that's plus 3 here. Right. So that makes sense. -2, -4. Yeah, that's right. This one is +1, +4, +3, -3. That's weird. Nitrogen bound to hydrogen can't have the same oxidation state as nitrogen bound to oxygen. That's what threw me. This is -3. This is +3. Okay, so yeah, we found it out. Let's see, +3. I'm looking at my answers there. +1. Yeah. Are we good?
Yes.
All right. Yeah, we've been at it for an hour and a half. We can keep going. Or if you're satisfied, you don't have to stick around. But I'll stay until the last student leaves. Are you thinking or finished? Let me see. Is there anything else? I'm trying to think back to results of this test to see if I recall anything where lots of people made the same mistakes. Let's see. Identifying reactions seems to be a problem for some.
Yeah, I don't mind to go over that.
Okay, let's see. Where did I put those? Down here. There might be some here. Let me back up into this part of the test. Yeah, here we go. Okay, I only put a couple in here. We talked about this one already. These are precipitation reactions because they're not oxidation reduction. We looked at the oxidation numbers for each one and found that there was no change in oxidation numbers from reactant to product side. So they're not oxidation reduction reactions. Acid-base reactions, they can't be because there's no acid here. Doesn't matter, even if there's a base, there's no acid. So it can't be acid-base. Acid-base reactions do what? Like this is our acid, and this is our base. They always produce that which is a salt and water. So if you don't have a salt and water on the product side, you can't have an acid-base reaction. We didn't talk about that in class though, did we? I think I'm saving that for the second semester. But you can still tell that it's not acid-base because there's no acid there, right? Acid, you got to start off with a hydrogen, at least one, and then the rest of the molecule. We don't have that. So the only one that fits is precipitation because we put two solutions together and we get a solid. That's precipitation. How about this one? Let's see, 23. Okay, so 2 aluminums and 3 bromines, 2 aluminums and 3 bromine yield what? Aluminum bromide? Yeah. 2 aluminum bromide, and this is a solid. So what type of reaction is that? That's a synthesis. You're taking simpler and making more complex. How about the second one? Let's see, silver oxide to silver oxide yields silver and oxygen. What's this one? It's the reverse direction of this type. This is a decomposition. So a synthesis in reverse is a decomposition, and vice versa. If we turn this one around, it would be a synthesis. Let's see, the third one, CH4 gas plus oxygen gas yields, let's see, 2 carbon dioxide and water. Oh, they must be doing it at such a temperature that water is still vapor. That works. Okay, that's balanced. Okay, what type of reaction do we have here? The best way to approach this one is to say, this is a combustion reaction because we're reacting a molecule with oxygen. And then we also know that all combustion reactions are redox, oxidation reduction reactions. Okay. Okay, so all of the following reactions can be classified as, oh, I missed the chance. When we go from 0 oxidation state to 3+ and 1-, that's definitely oxidation reduction. The other key to this is if you have elements on one side and that element ends up in a compound, that's definitely oxidation reduction. So element compound or compound element works both ways. That saves you the trouble of having to calculate oxidation states. You can recognize a redox by that fact. So they're all redox reactions. Let's see. We did that one already. Can you tell which one of these is insoluble in water? Yeah, just go to your chart, right? You know how to read that chart with the gray boxes in it? You just look at this, the cation down, let's see, is it across the top? I think it's across the top. And the anions down the left and find out where they meet. I'm sure that was on the test. It was available, right? Last page. Yeah, flip it over. Is that all there was?
I mean,
There should have been another one.
there,
That one right there, yeah. That's it. So all you have to do is just take the cation. They're across the top, aren't they? Yeah, cations across the top, find your cation, then find your anion on the left, follow them down where they meet and see, is the box clear or gray? If it's gray, you got to precipitate. Or if they're all clear, then they're insoluble in water. They're soluble in water. Following salts are insoluble in water? None of them. All of those salts are soluble in water. Now, if you knew the rules, you know that the alkali metals are soluble in water. So the sodium salts, the potassium salts are all soluble. All nitrates are soluble. So lead nitrate is soluble. Lead 2 nitrate is soluble. Calcium chloride, that is a soluble halogen compound of an alkaline earth. Now, not all alkaline earths are soluble. And not all chlorides are soluble, right? Silver chloride is a good example. It's insoluble in water. But you can either use the chart or memorize the rules. That's why I gave you the chart, so you wouldn't have to do that. Memorize. If you guys we're all going for bachelor's in chemistry, you'd memorize the rules. But since you're not, let's see. Do we have anything else in here that would lend itself to types of reactions? Those may have been the only two that I used out of all those review document selections. Can you tell can you determine the limiting reactant in a binary reaction where you have two reactants gives you products? Tell which one's limiting.
That usually is the one that runs out, right? But how?
Right, the one that runs out first.
Okay.
And there are several ways to approach the problem. The foolproof way is to calculate product based upon complete use of one of the reactants. And then take the second reactant and say, convert it completely to product and compare the product values. The one that has the smallest amount of product leads you back to the limiting reactant. That one works every time. There are other ways to approach it, but that one is foolproof. Stoichiometry, well, that we're sort of on stoichiometry. With limiting reactants, we're talking stoichiometry. Is that everybody comfortable with that? Right. First, you got to write the compounds correctly. Then you have to be sure the equation's balanced. Then you have to see what are you given and put that on your balanced equation and say, all right, is that in moles or is it in grams or is it a solution? If it's in moles, you're off to the races. You can go from one place to another place in that equation at will. But if it's in mass, you have to convert to moles. If it's a solution, you need the concentration and the volume, right? Usually something like this. Right? So if you want moles, you multiply molarity times volume equals moles. And once you got moles, then you can move. Stoichiometry and equation is all based upon numbers, moles of reactants and products. So if you're given mass, you're stuck with a balanced equation until you convert mass to moles. Can't do stoichiometry with anything else but moles. Let's see. Everybody okay with balanced equations, or you want to take a difficult one?
Can we try a difficult one?
Yeah. How about this one? Number 14. Okay, so what's the coefficient of oxygen when the following equation is balanced? Right, we have ammonia as a gas and oxygen as a gas producing nitrogen dioxide as a gas and water as a gas. So that tells me that the reaction conditions are greater than 100 degrees Celsius because our water is turned into a gas. Okay, so we want to balance that equation. Let's see, we don't have any polyatomics that we can preserve. We do have a single element, so we're going to hold that one until last. But we need to assess first. So we got nitrogen, hydrogen, oxygen. Nitrogen, hydrogen, oxygen. And our assessment is 1 nitrogen, 3 hydrogens, 2 oxygens. And over here, 1 nitrogen, 2 hydrogens, and 3 oxygens. Okay. Let's see. That one has oxygens in 2 different places. But we're gonna save oxygen to last anyway, so we don't worry about that. So we're going to hydrogens because we have to hold oxygen till last. So this is the only other one that's not balanced yet. If we've got 3 hydrogens on this side, but 2 on that side, how do we do that? Well, actually, there are 2 ways you can do it. You can use a fraction over here, right, to do it. But that might get confusing. If you've got an element in one place on reactant side and one place on the product side, and you've got odds and evens, cross multiply is a good technique. So we would take this 3 and put it over here. And take that 2 and put it over here for the hydrogens. Right? So that gives us 2 nitrogens, 6 hydrogens. And this gives us 6 hydrogens and 3, 4, 5 oxygens. Okay. Okay. All right. So we need 2 nitrogens on this side, right? So that gives us 2 here. Now we've got 4 plus 3 is 7 oxygens. Now we can balance the oxygens. So how do you get 7 oxygens out of a diatomic? Use a fraction. 7 halves. Good. If you take half of that oxygen molecule, you got 1 oxygen, right? Times 7. That's 7 oxygens. Okay. Now we got to finish it off because we don't like fractions in our coefficients. So how do we get rid of that fraction? This ratio is fixed now. This is balanced, technically balanced. 2, 7 halves, 2, and 3. But we want whole numbers. So if we want to get rid of that fraction, we multiply by the denominator. So 2 here gives you 4 there, gives you 7 there, 4 here, gives you 6 here. So our coefficients are 4, 7, 4, and 6. And the question was, what's the coefficient in front of oxygen? 7. It takes practice. There are some equations that I won't even tackle. They just, in fact, some of those equations that are have massive numbers of reactants and products could end up with 1,000 for a coefficient. So what researchers do in that case is they have a computer algorithm do it for them. And it just what's the proper term? It just bulldogs its way through. It tries this set, and when it gets in it, the program says you're getting close, so it modifies it a little bit, and you're getting closer, it iterates to the final product.
I have a question on that one real quick.
Okay.
You multiplied just the first part of that equation by 2. You didn't multiply the end product, right?
But when I did this step right here,
Yes.
no, I did the whole equation.
Okay. Okay.
It was originally balanced with 3, 2, 7 halves, and 2. I wanted to get rid of the fraction, so I used a 2 multiplier. And we can't change the ratio now. Once it's balanced, we can multiply by any number we want, right? It's goes back to math. Right? Do the same thing to everything in the expression, and you haven't changed the ratio. So the ratio was 2, 7 halves, 2, and 3. If I multiply by 2, Now this becomes 4. This gets rid of the fraction. Leaves us with 7. That gives us 4, and that gives us 6.
Okay, thank you.
Right? Well, what do you think? Need to think for a couple of minutes and see if there's anything else that strikes your fancy. First rule of chemistry, stay hydrated. And let me see if anything flips my switch here.
Question 18, how do you know it's like a compound with strong base?
18, oh, 2 more. Here we go. Which of the following is not a strong base? Is that the one? Okay. So we've got A, B, C, D, E. And we start off with calcium hydroxide. KOH. Ammonia. Lithium hydroxide. And strontium. For this one, to say which one is not a strong base, since we haven't talked about, second semester, we go into more detail with acids and bases. So at this point, it's process of elimination. If you know what strong base is produced from, then you can eliminate those, and what's left over is the weak one. Right? So alkaline metal hydroxides are all strong. Alkaline earth hydroxides are also strong. So there's an alkaline earth, there's an alkaline metal, there's an alkaline metal, and there's an alkaline earth. All these hydroxides are strong. That leaves the weak one. Ammonia is a weak base. Now, notice it doesn't have a hydroxide in there. We're going to talk about that second semester. Right? Why that is? It's still a base, right? Because you stick litmus paper in there, and it'll turn blue. Question?
Kind of, I'm taking human anatomy, and one of the chapters we went over talked a little bit about the acids and bases that you can find in the human body, and I thought the bases would all be hydroxides, hydrogen, oxygen in there. I guess I just didn't realize ammonia would be a base because it just had the hydrogen atoms in it.
Right. Well, I'll give you a teaser for next semester. These are in aqueous solution, right? So water is a reactant, and lots of it, right? So when we react water with ammonia, water transfers, it acts like an acid. It loses a hydrogen, transfers the hydrogen over there to ammonium, right? It leaves its electron behind. So its electron now is possessed by what's left over, O and H, only one H left over. That's why it's a base.
Okay.
And that happens a lot in the human body too. Yeah. In fact, a lot of the molecules in the human body are amine based, NH2 groups, and they will accept hydrogens like this from water, and that produces the basic outcome. Yeah, I stole some of my thunder for next semester there. I think part of the problem is time related. Time on your end for, absorbing the material and working the problems. Time on my end so I can spend enough time in class to cover the topics adequately. So that's why we're having a tutoring session, make up the difference. Now, we had a lab Tuesday, right? I don't think you were here, were you?
I was
Okay, so you get in touch with somebody that was here and get the data for Boyle's Law. Let's see. Who was here? Here we go. Zoe was here. Kaylee was here. Olivia was here. Matthew was here, right? Yep. Augusta Redden was here. And Xavier was here. So if you can con one of them giving you the data, then you can finish the report.
I'll bump the information off that somehow.
Okay. All right, how we doing? Let's see. Class starts at 12:30 then. For today, 12:30. Yeah, 12:30. So if we broke now, we'd have an hour and a half for lunch. But we can stay another half hour or so, right? If you have some other questions. Is there anything that's not on the exam that you want to talk about? Or did you all just come with that in mind, right? How did I miss this question? Okay. Are you comfortable with diluting concentrated solutions to a known concentration?
Did go over that.
Okay, how about this one, 21? Right. Okay, so the formula you're going to use here is sometimes you'll see it this way: M1V1 equals M2V2. Molarity times volume equals molarity times volume. Or you might see it this way: initial, final. No, my mistake, not that way. Concentrated and diluted. There we go. Now remember why this works. Because when you take this much volume out of your concentrated solution, it gives you a certain number of moles, doesn't it? Right? Because M equals moles divided by volume. So volume times molarity is moles. So this gives us moles of the solute from this side of the equation. Well, they're the same value. When you take that volume and this many moles, you put them in your dilution vessel, you still have the same number of moles. So on that side, you're going to have a new concentration, the one that you're targeting, and the volume of your device, right? Usually a volumetric flask. So there we have this, and those are equal. So that's why this equation works, because the moles don't change when you move them from here to here. Okay, so now if you're going to use this equation, you need to set up a little table. Like this. And read your problem and put the values in here where they belong. What volume of 18 molar sulfuric acid that's definitely concentrated. Sulfuric acid, 18 molar, that'll eat your hand off. Must be prepared, must be used to prepare 2.3 liters. That's the final volume. Of what concentration? 0.145 molar. So there's your unknown. That way you can find out, all right, that's where I'm headed. And then if you take this equation and solve for that value, you're going to have the diluted over concentrated. Now you can just plug the numbers in and you're off to the races. You just have to be sure. Well, actually for this ratio, you don't have to change the volume to liters because they will cancel each other. Right? So you can use milliliters here. You can use cubic feet, use any value. But whatever you start with is what you end up with. So once we started out with liters, this is going to be in liters. All your answers are in milliliters. Oh, that's messed up. There's no answer for C. It's something times 10 to the third. Okay. All right. Okay, so if we put those values in, 0.145 molar times the volume of the diluted, 2.3 liters, and then the concentrated molarity is 18 molar. So see, the molarities cancel and would leave us with liters. And it should come out to actually, this is going to come out to 0.019 liters. And then to convert that to milliliters, right? Units are going to get smaller, right? We're going from liters to milliliters. That means the number has to get bigger. That tells you which way to move the decimal. We got to move the decimal this way, right? How many places? Thousandths place. 1, 2, 3. So that's why it's 19 milliliters. Or the way I worked it there, I went ahead and changed the volumes to milliliters first. Instead of 2.3 liters, I changed it to milliliters. And then the answer comes out as milliliters. Either way works. So if you're asked to do a dilution in the lab from a concentrated solution, that's the way you do it. And the ratio in this, if you have a solution, concentrated solution that's made up of several components, then they're going to stay in that same ratio after you dilute them. They'll just all be lower concentrations, but they'll be the same ratio. Okay. So we did those already. Any others that flip your switch? We did those already. A couple people got this one wrong. All right, how many of these, how many of the following are true concerning balanced chemical equations? Only one of them is still true. Atoms are neither created nor destroyed. The rest of them are worded kind of wonky and they're just not true. The number of molecules is not conserved. The number of atoms is conserved. Number of atoms of each element is conserved, but not the number of molecules. Well, let's see. See if there's anything that flies out at me. This problem 33 uses oxidation numbers to help you balance the equation. Right. We're going to take that further in the second semester, but this is a very simplified version. Did that give you anybody any trouble?
Which one
No.
was it? Sorry.
Yeah, go ahead.
I'm sorry. What was it that you asked?
I just asked if number 33 gave anybody trouble.
I mean, I missed that on the quiz, so
I'm sorry?
I missed that on the quiz, yeah.
Okay.
I did as well.
All right. So let's see. We got iron, elemental iron, and bromine yields a 3+ ion for iron and a 1+ ion for bromine. Okay. Now we can tell immediately that this is a redox reaction. Well, the problem says it is also. But we want to balance it and find out what the coefficient is on the bromine. So when you have a redox reaction that's not complicated with water molecules and hydrogen ions and that type of thing, because we're going to deal with that one in the second semester. But this is a simplified version. What we can do is we can use tie lines to show movement of electrons, because when you balance a redox equation, a primary requirement is that the number of electrons that leave some species are the same number that arrive somewhere else. Okay. So this iron is going to go from here to here. Right? It started out as oxidation 0 and went to 3+. So how did it get there? If it goes 3+, it has to lose 3 electrons, right, for each iron. So this is a loss of 3 electrons per iron atom. And we're saying it's lost from this one to produce that one. So this one loses 3 electrons. That means it has 3 more protons than it does electrons and makes it 3+. Okay. So bromine, for each of the bromines, right, since each one of these is 0, it gained 1 electron per bromine atom. Right. We have 2 of them over here, but we're going to deal with that in just a minute. Okay. Let's see. All right. We can take several approaches to this, but I think first I want to say, all right, if we got 2 bromines here, we're going to need 2 over here anyway. So that means 2 bromines gives us the movement of 2 electrons for that group to these 2, right? 2 electrons. Whereas this one moved 3. So how are we going to balance the electron movement? If this one lost 3 for each iron, and this group gained 2 to get to that point, how do we deal with that? It's odd and even. Whenever you see odd and even like that, think cross multiply. So if we multiply this one by 2, that's 6 electrons. And multiply this one times 3, that's 6 electrons. So what does that 3 mean? Or what does that 2 mean? That 2 means 2 here, and 2 here. Right? 2 irons times 3 electrons each is 6 electrons. And this one, we started off with 2 and ended up 2 here, but we're going to multiply by 3. So 3 times this one is 3 here, and 3 times this one is 6 here. So look at it this way, 6 bromines, 1 electron gained is 6 electrons total. So now we're balanced. We have 2, 3, 2, 6. So the coefficient in front of Br minus is 6. I had some people, let's see, one who discovered the essential nature of acids through solution conductivity. That was Arrhenius. We didn't hit that one too heavy. I'm sure it was in your textbook. So that threw a curve at some people. Some people even got this one wrong. I think the people who got this one wrong didn't read the question. Give the empirical formula for the following compounds. So you count up the carbons, you count up the carbons, got 6 of them. Count up the hydrogens, got 6. So C6H6 is the molecular formula. The empirical formula is CH. The ratio is 1 carbon to 1 hydrogen. And similarly for the rest of them. You determine what the molecular formula is and then see, can I reduce it to the simpler whole number ratio? And this last molecule is like C6H12O6. And the simplest ratio there is 1 to 2 to 1. 6 to 12 to 6 is 1 to 2 to 1. You just divide through by 6. Okay, and the rest of these are bonus. Any others? Now this is all being recorded. So I'll post this in Brightspace. Try to get it done this evening in case people that missed the meeting can have a look at it. Or if you think your notes, you missed something in your notes, you can go back and look and see. Nothing else attracts your fancy?
I think I'm okay with the review for now.
Okay.
Thank you.
We'll reconvene at 12:30 for gas review, gas chapter review.
Okay. And can I ask, besides doing the homework, I really would like to just keep working on problems. But I feel like whenever I do the homework assignments online, I can only do those so many times. I was just wondering if there's more stuff we could practice.
Oh, yeah. Yeah, I gave you the review document.
Yeah.
It's got a ton of problems there. In fact, there's lots of repetition. So if you're short on time or energy, just work every other one. Yeah, the exams are based off of the review document in terms of types of questions you're going to encounter. So if you're comfortable with the problems in the review document, you should have no trouble with the exam.
Okay.
And the only way to get comfortable in my book, right? Some people, I mean, just have a knack for it. I'm kind of on the fence about that one. I get comfortable with stuff by doing it a lot, doing the same thing a lot in different ways. That's how you learn chemistry, actually. Work lots of problems. Because that's the way nature comes at you. Right? It doesn't pull any punches. It comes in from this way and then it comes in from that way. And there are similarities, right? It may come in this way or that way, but the problem is solved exactly the same way. But you wouldn't know that unless you solve problems in both scenarios. Okay, we'll cut it off now and come back at 12:30 and talk about gases.